Okay, in your snap booklet on page 131, it starts to talk about molarity and concentration. Okay, so we're going to use this simulation again to help us understand exactly what they mean. Let's first talk about molarity in like what we knew in Science 10. Okay, so before we get into this, let's just kind of recap. When we were looking at number of moles in Science 10, we were always talking, well, we weren't always talking about a solid because they often, you know, use other examples just to give you some more practice. But you should always be looking at solids here or pure liquids. And so you looked at a mass divided by the molar mass, where this was mass, and mass is measured in what unit?
Grams.
Very good, grams. And big M is molar mass, and its unit, which is in the data booklet, is in grams per mole. Very good. Okay? And for those of you that hate memorizing this formula, you can always go with this formula. Molar mass, big M, is in grams per mole, which is in your data booklet under the key section. Grams is mass divided by moles is N. So big M equals little m divided by N, because the units say so. And actually, scientists don't really have formulas. We have units. We just look at the unit and figure out where we want to go with the unit, and put our numbers in. So I'll put the number of grams, I'll divide it by the number of moles, and I'll get my molar mass. Okay? But sometimes we like formulas because we just like to plug the numbers in hair calculators, buttons, right? So, happy? Makes sense? Mass is equal to, but I'm going to use this formula because those of us that have memorized it, which is like 98% of people in here like this formula. But if you ever get stuck in an exam and your mind goes blank, right? And you kind of go, well, I don't remember what it is. Use this one. Because it's the same thing, just rearranged. Okay? All right. So, when we're looking at mass and molar mass, we actually have, if we're looking at mass, we're actually looking at a pile. I'm just going to change this. There we go. We're looking at a pile, and the pile has a mass. And let's call this mass 1.00 grams. And in that 1.00 grams, there are a certain number of circles, right? Like 6 billion trillion circles or something like that. In fact, let's pick this to be carbon. This is a lump of coal, and the lump of coal weighs 12.01 grams. Well, I picked that exact number because the molar mass of carbon is 12.01. So this is saying that I've got exactly 1 mole in this pile, which means I have 6 billion trillion circles of carbon. Carbon atom, carbon atom, carbon atom, carbon atom, carbon atom, 6 billion trillion times. It would take me a few generations to draw all those circles. That's how small a little itty bitty atom is. Okay, so 6 times 10 to the power of 23 little circles in my pile. Is that ever going to change? If I pick that pile up and I put it over here, will it change? If I pour water on my pile, will it change? No. First of all, carbon isn't going to dissolve in water. Okay? But second of all, even if it did dissolve, what happens to that pile? It's spread apart. Right? So let's pick no longer carbon, but let's pick NaCl. And NaCl's molar mass, or let's pick NaOH. No, let's pick NaCl. Come on. Because we've been using it a lot. Somebody tell me the molar mass of NaCl. 23 and 35 makes 50 something. You're going to need a calculator because you've got a few decimal places there. There's a calculator right there. Pardon me?
I don't know. I didn't even look at those masses actually.
Let's go long. 58.44.
58.44 grams per mole is the molar mass of NaCl, and therefore I want that pile to be 58.44 grams. because I want this to have just 1 mole. 1 mole equals 58.44 divided by 58.44, so 1. So the math works, our understanding works, and then we have exactly 6 times 10 to the power 23 circles of NaCl. Of NaCl.
Smash.
NaCl. NaCl. Okay? Right, so, where was I going with that? Oh, if I have 6 billion trillion circles in my pile, and they're in here, 6 billion trillion circles, or 58.44 grams, and I shake that pile out. 10, 20, 30, 40, 58 grams. Okay? So there's my pile. What happened to that 58 grams?
Dissolve.
It's dissolved, but is it still there?
Yep.
Yeah.
It's still there. It's just dissolved, moved away from each other. Different form, I broke the ionic bonds, they form bonds with the polar water. Yeah, we know all that. But I still have the same number of circles that came out of that shaker are in here now. Okay, and for ease sake, let's stop talking about 6 billion trillion, and let's talk about some number that we can understand, and let's say 12. 20, let's say 20. 20 circles came out, 20 circles are in here. Actually, that's not true. 20 NaCl's came out, and therefore I have 20 Na pluses and 20 Cl minuses. Right? I'll show you. Reset. Just one shake. With a pause. Pause.
Precision.
Okay. Look at that. I wouldn't be able to do that twice. Okay, count the greens. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 greens. What are the greens?
Chloride.
Chlorides. Oh, why did I write 7? 9 Cl minuses. How many reds? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 reds. Why? Because there are 9 what? NaCl's. Yes? And in fact, in our dissociation equation, what we have written, NaCl is going to become Na plus and Cl minus. Yes? And so wouldn't 9 NaCl's become 9 Na plus and 9? Right? And here are 9 NaCl's. 1, 2, 3, 4, 5, 6, 7, 8, 9. I had to draw a circle around NaCl, 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 right? NaCl, NaCl, etc. And let's let it hit the water. Ba-da-da. And, oh, they're overlapping. Hold on. There you go. And sure enough, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 greens. Separate from 1, 2, 3, 4, 5, 6, 7, 8, 9 reds. See that? So I actually have 18 circles. Okay. What's the matter, Austin?
What kind of sorcery is this?
Okay, think of it this way. Austin's not so happy. In fact, Austin's so mad about this. Austin's so mad about this that he takes his Lego airplane. Okay? Lego airplane. Built out of one airplane. One airplane. And he smashes it on the floor. And what happens to all his Lego airplane? Lots of little bits. There are 3 red bits and 28 gray bits and 2 black bits and, right? One airplane made lots of bits when it broke up. But we can say one airplane was divided up into. Okay? Or we can say all those bits are needed to make one airplane. Okay. Right? Okay. So not sorcery, logic. Logic. It's a beautiful thing. Okay. Everybody happy with the concept that not just the circles, but the number of moles. So Austin's one airplane that was smashed into, I can't remember how many red bits I said.
Three.
Three red bits. That's some good listening
26
skills.
gray, yeah. 2 red and 2 black.
28.
Okay, come on. All right, so this airplane that was smashed into lots of little bits, what if Austin took 2 airplanes? Okay. So it would just be double of everything. If I said 3 red bits before, how many red? Yeah, they're exactly the same.
6.
6. Because it was a birthday party, and you always get double presents at birthday parties.
Never had.
So 6 red bits now instead of 3. Everybody okay with that? Okay, these bits, boys, bring Booker in, come back, girl. These bits are not airplanes in these examples, but and they're not even circles in real life. Because in real life, I started by talking about that pile, and it would take me 3 generations to draw all those circles. So they're teeny tiny. There's no way you could actually see these circles. There's no way I could sprinkle out just 18 circles or 9 NaCls from here. There's just no way. So it's more likely that I've sprinkled out a mole and got a mole of Na pluses and a mole of Cl minuses. That's more likely. Like 23 grams. Or no, 58 grams we decided. Right? It's more likely that I sprinkle out 5 moles and then have 5 and 5 dissolve. And wouldn't it be great if they used whole numbers the whole time, but they're not going to. You're going to sprinkle out 1.28 moles, and you're going to get 1.28 and 1.28 moles. Everybody okay with that? Okay, so the number of moles in my solid doesn't change even if it's dissolved. That has nothing to do with concentration. Well, it does, but okay. So let's say shake, 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 shake. Oh yeah, it's paused. Say. I want to make this a certain color. So you kind of like, you conceive this as Mio juice if you want to think of colors. You know, squirty, squirty Mio. Isn't that what it's called?
Yeah.
As opposed to shaky, shaky salt. Really technical terms today. Okay, so shaky, shaky salt comes out. And the color of this is still going to be colorless because it's just salt. But let's assume it's you guys made copper sulfate a couple days ago, right? And you put in 1 scoop, 2 scoops. And the color of that was a
Blue.
light or dark on your
Dark.
first scoop?
Oh,
Your
light.
first.
Light.
Light. You put in another scoop and now it's
Darker.
darker. Let's call it medium. You put in a lot more scoops and now it's
Dark.
darker. Why?
The concentration.
Concentration increased. The number of moles per, actually per your volume. See, watch. Okay, so let's call this a light color. In fact, the computer can't really see this. I'm just going to take off one of these lights. Let's call this a light color. Okay, light. Even though we can't call it NaCl anymore, we'll call it copper sulfate. Okay, so the greens are sulfates, and so it's copper sulfate. And this is a light blue. And if you were to shake some more out, I push pause again, you are now having that medium blue. And the number of moles in here has increased. But your volume is the same. What would happen if I increased both of them at the same time by the exact same amount? It would stay the same color. So therefore, I have to say it stays the same concentration. Okay? So concentration has to deal with 2 things. Number of moles, or how much I've shaked out, and the volume, per the volume. Boys, what's the matter? Huh? What's the matter? It's all good. Not sorcery, logic. Concentration has to do with 2 things. The number of moles, and in that number of moles, how much volume have I got? Number of moles per 1 drop, number of moles per 1 bucket. They're very different. The color of that would be different. The number of moles would be the same, the number of circles would be the same. So here's one drop. Let's add some water to this. The number of circles is still the same. But it's now lighter in color. Right? So you know when you're making iced tea at home and you put in your sugar, which is just sugar, by the way, flavored with a bit of chemicals. And you put it into your water, right, and stir, stir. Has your mother ever said to you, that's too concentrated? Right? Come on. Yeah. And so, because they don't want you to eat all that sugar. It's too sweet. So they make you add water to it. Except for, you're still drinking the same amount of sugar as you were before, Mom. It makes no difference. It's just one tastes a whole lot better. Right? But it's the same amount of sugar. So really, your mother has to say, it's too concentrated. Pour out half of it. See, there go the moles. And now add some water. See? I know, my poor kids to have me as a mother. I know. I know.
Where are these numbers coming from?
There's like the
Right?
I got serious my whole life now.
You guys pour half of it out, so there goes half of the moles of sugar, and add some water to it, and now you're drinking less sugar. Get it? Okay, because the number of circles in there is still the same. Yes?
So if you were to add something to water, like, say like iced tea,
Mhm.
at what point would the substance that you're adding in affect like the volume?
None.
Never?
Never. Your volume does not change when you add the salt to it. Well, actually, that's not entirely true. When it changes is when you can't dissolve anymore. Okay? So if it's saturated, and now I'm actually adding a solid that sticks to the bottom, you might as well just add a rock. And when you're adding a rock, the space that takes is currently occupied by the solution. See, I've got solution there. So the that solution has to get out of the way of that rock, because the rock is occupying that volume, that space. And so if it's pushing up, and then this pushes up, and then this pushes up, then that raises. So like there's a logic thing about a bird that can't reach his beak into the barrel of water. Have you guys heard this?
Yeah.
So there's a crow, and he can't reach the water, but he's very thirsty, because every time he sticks his head in the barrel, he can't reach all the way down. But he's almost there. His beak's almost touching it. So how does the crow go about getting the water from the barrel? Well, he goes and picks up a rock and drops the rock in the barrel, and goes back and gets another rock and drops enough rocks in the barrel that the water then rises. And now he can drink. And why can he drink? Because the water has been displaced by those rocks. That rock is taking up a space. Right? If I put a big mountain in between you guys would have to move out of the way. Right? You're all crammed into some tube in London on a holiday. You guys don't go. Sea train. Sea train. You're in a sea train, right? And you're crammed in there because it's Stampede Week and like this. And no one can move. Right? And then, I don't know, the rodeo clown gets on. Right? With his big rodeo clown suit and the big ring around his stomach, the hula hoop that they have in their costumes. Right? And he gets on. Well, everybody's going to have to move out of the way. They are displaced. Okay? And then therefore the volume expands. So only when you've added enough iced tea that you're now actually adding solid to the bottom. Will the volume go up, or like the level of liquid go up. Okay? Okay. Thanks for the sideline. So concentration deals with two things. The number of circles in there and the volume of water. If I change the volume of water, it changes the color, the concentration. And if I add more moles, so your mom leaves and you just go ahead and shake some more in there anyway. Don't ever do that. That would be very naughty. So you add more in there and you now have a higher concentration again. Okay? So, number of moles divided by volume is concentration. So we have a formula. And we have units. Concentration's units are number of moles. What's
Mole.
moles? Mole or N. Yeah, I'll put both of them in. What's volume measured in?
Liters.
So moles per liter is what concentration is. Concentration is moles per liter. And the formula is N divided by V. Oh, simples. Only, you know how before we memorized N as little m over big M?
Yeah.
And then I used the units of big M to try to convince you of a different formula?
Yep.
We kind of don't memorize it that way. We normally memorize it N again equals C times V. I don't really care what formula you use, as long as you know what to do with your numbers. Okay? So a lot of people like this formula because they've memorized moles per liter, and then N divided by V makes sense to them. Perfect, good, use it. And a lot of people memorize this because it's all on one line and the algebra's easier. Okay, fine, do that too. Okay, whichever one you fancy, really. And this is for solutions only. Oops. And this was for a solid or a pure liquid. So I can't use N equals C times V if I'm talking about weighing something on the weigh scale back there. Because that doesn't have a concentration. How many circles per liter? No, it's just how many circles. But if I take that and I put it in water, oh, that'll have a concentration. Because if I put in a little bit of water, it'll have a high concentration. If I put in a lot of water, it has a low concentration. Does that make sense? So quite often, we figure out how much mass you have to take on the weigh scale in order to calculate concentration after the end. Okay, you guys are saturated, I can see. You are done learning today. Okay, so we're going to do something else right now.